dimensions separately and solve them completely independently of each other. So you don't even have to worry about the two-dimensional problem. You can actually just look at the list of street numbers and then the list of avenue numbers and solve them both separately and then add up the results. So then how do you solve the 1D problem? And it turns out that if you actually just sort the points and scan them from left to right, okay, then if you're at a certain place and there are, I don't know, let's say 10 points to your left, well, every time you move one step to the right, then you're adding the total distance for by another 10. So if you know how many things are to your left and how far you move from one point to the next point, you can use that to update the running sum so that you don't have to actually do all the pairwise distances. And in fact, the scan from left to right, once you have the sorted, the 1D points can be done in linear time with some clever arithmetic. The only thing that I don't know if anybody got trapped in is, I believe that you actually need to use 64-bit integers if you don't want to get overflow. But for the most part, I think most of the incorrect submissions are time limit exceeded, which is probably somebody trying to do the n-square version. Any questions and discussions about this problem? Okay. Arithmetic decoding. So this problem, it looks a little bit scary at first, maybe because there's math and probability involved, but actually it is not that bad if you just follow along. So what you do is you're given a number and you basically have to figure out what message it encodes based on some subdividing of intervals recursively as given in the problem statement. So what you can do is you can basically follow along. You start with the interval that they gave you, 0, 1, and use the formula to figure out how you cut the interval. Okay, so this is all can be done easily. And then if the number that they give you is less than C, then the first letter is A, otherwise it's B, and then you update the interval exactly as described in the problem statement. And then when you're at the end, after you decoded n symbols, that's exactly the message, and you're done. Now, you can also, if you don't like that, you can also try all possible input messages because n is only up to 15. So there are only at most 2 to the 15 possible input messages. For each one, you can do the encoding as described, and then basically compare the encoding against the inputs and see if the two are correct, the matching, and then you can figure out which original message it was. Now, the judges actually we try to be nice, and there's a reason why things are in binary and the probabilities are something out of 8. And we have actually chosen everything so that if you just use double precision, floating point numbers, and use exact comparisons. So you don't have to use epsilons when you compare two things. If you just use exact comparisons, everything can be done exactly, even though we're using floating point numbers. And that's based on the property of the way floating point numbers are represented. There are a few submissions that I saw that actually got things wrong when you try to use epsilons to check things being equal, but then you didn't use the right epsilon. You used an epsilon that's too big, and then you end up getting things wrong. So there's some teams I saw that try to, I guess, be a bit smart with the floating point comparison, but I guess it was only a bit smart and not quite smart enough because they used the wrong epsilon. If you use the right epsilon, you can actually make it work. But in fact, if you just do exact comparison, it would also work. So that tripped up the field teams, but I think most teams that tried it at the end eventually got it. Let me just check the standings if that's true or not. Most teams that tried eventually got it. Yeah. Any questions about this one?
So Howard, I think I'd just like to make a comment. I don't know, for sort of the academically younger teams, the issue or the difference is doubles are represented in base 2. And so if the denominator is always a power of 2, which 8 is, then the numbers are exactly represented so long as in IEEE floating point, I believe you get 53 bits of precision. And so long as everything can be represented that way, you lose nothing, you get exact representations.
Yeah, that's exactly right. And in fact, the number, the size of the message, 15, was chosen to make sure that happens. Um, we went through a few iterations of this problem, and at the beginning, we actually have n being up to maybe 1,000, I think. And of course, in that case, you have to do something a bit smarter than just using double, or you can use Python, I guess, which has arbitrary length integers. But we scaled it back to n equals to 15 precisely for this reason, that the floating point arithmetic, as long as you use doubles or long doubles if you wish, will represent everything exactly. If you use float, the single precision, it will not be enough. Yeah, we checked that. Any other comments or questions? Okay, the next one. Now, I don't know. I mean, I didn't write anything on my slide because I don't know if there was much to say. It was a bookkeeping exercise. You have to keep track of how many people in each group got infected and how many people in each group didn't get infected, and do a relatively simple computation. Um, I don't know. Is there anything that anybody want to say about this problem? Again, let me just look at this. I think everybody, 31 teams got it. So everybody that got at least one problem in the contest got this problem at the end. I think there were some problems. Some people have, instead maybe a strict comparison in the less than equal to comparison when you decide whether something is effective or not. So for example, if the number of the infection rate with or without the vaccine is exactly the same, some people write 0% effective instead of not effective. But I think for the most part, that's the problem. If there are any error, any incorrect submissions. Anything anybody wants to ask about this? Okay. Yeah, I think everybody that got at least one problem got this at the end. So maybe there's not a lot to say. Conquest. This one, what did I say? I thought that this one was a big surprise for me and also everybody in the judging room, I think, because there were a lot of incorrect submissions, and they are usually either time limit exceeded or memory limit exceeded. And the reason why we were surprised was that the people that got this response are usually people that actually know what they're supposed to do. They just didn't do it right. Okay, so what's going on here is that you have this spanning nation that starts at item number 1 with a certain army size, and they can attack any adjacent islands as long as their army is smaller than the total army size of the spanning nation. And if you attack, then you eat up the army, and then your army increased by that amount. So basically, what you have to do is you have to keep track of who are all the potential islands that you can attack. Who are you adjacent to at any one point, and then you can attack them in any order. So you might as well attack the one that is smallest in terms of army size, because if you can't attack that one, then you can't attack anybody else, and you have to stop. So it's pretty common that you maybe use, let's say, a priority queue of keeping track of all the reachable islands. And then the one with the smallest army, which is the top of the priority queue, you just look at it, and if you can attack it, then you attack and you eat up their army, and you just keep up. And every time you attack and eat up an army of an island, then you can then go and insert all the neighbors of that newly conquered island, and you just keep going, right? And when you're done, when you can't attack anymore, then you're done. And if you are familiar with standard algorithms on graphs, this is actually very much like Dijkstra's algorithm, right? In Dijkstra's algorithm, you maintain a list of reachable adjacent adjacent nodes that are adjacent to, I guess, nodes that you have processed so far. And then you use the priority queue to keep track of the one that is closest to you, and then you keep picking that one. And I think many of the people that submitted wrong solutions actually have this idea, and they even use priority queues, but a lot of people ended up having time limit exceeded, memory limit exceeded, and so on. And the issue with, I think all of the issues is that when you prims, Dijkstra's, oh yeah, sure. I guess that you can think of it either way. Yeah, I guess for some reason I thought about it as Dijkstra. Anyway, it doesn't really matter. It is all about this inserting things, the adjacent nodes into a priority queue and picking the next one. Okay, so what is the problem? The problem is that many people, when you insert a node, into the priority queue, you don't immediately mark it as inserted. So some people end up inserting a node many, many times if that node has a high degree, and that blows up the algorithm in terms of memory limit. And I think everybody that's got memory limit error, it's because of this.
Yeah, that or a very related issue where they would avoid inserting if something was marked, but they wouldn't mark it right away. So a simple solution that would fix almost all versions of this issue we saw was as soon as something comes off of the priority queue, then you mark it. There might be slightly better versions than that, but even that simple solution would have worked. But many people didn't mark it when it came off the queue.
Yeah, so the issue was basically that some nodes get inserted many, many times. So essentially, people have the right algorithm, but the implementation was missing a little bit. So this one was a big surprise to us. We thought that it's a variation of a relatively standard graph algorithm, but unfortunately, people recognize it but didn't quite implement it right. Okay, so I'm gonna stop the sharing and let Zach take over to the other problems.
So sorry, I'll interject a little bit again for maybe the younger kind of crowd academically again. So the idea of a priority queue is the idea of a queue where there's a priority list, some sort of value or sorting that is that the priority queue allows for efficient insertions and extraction of the top of the queue.
Yes, good. Okay, so I'm going to finish up with the last few problems, and this is certainly into the harder portion of the contest. First, we have interview queue, so we're presenting them in order of first solved, but this one was only solved by 2 teams. The idea here is you can all picture what happens every round. The people that are adjacent to someone else who has a higher rank will leave the queue, but you have to do this efficiently. We saw many submissions that just tried a straightforward simulation that scanned through the list of remaining people each time. So the entire list, marked off the ones that needed to be removed, shortened the list, and then repeated again. The problem is that there can be examples like this. And you get the picture. So each round, only this person would leave the queue, but you would still scan all 100,000 entries. Then the second round, only this person would leave the queue because they are beside 2, and you'd still scan all remaining entries. So that's a quadratic solution, O of n squared. And that wasn't fast enough for this problem. The best approach, well, like a much faster approach is to make the following observation. Sorry, let me quickly get a more helpful example here. So the first time through, when you mark some people off, so we're 1 is going to leave the first time, as is 2, and as is, okay, this isn't a good example. Here, let me make this one. There, I'm just coming up with a good example on the fly. So these 3 would leave the first round because they are the only ones besides someone that's larger. But now, look, we don't have to examine this 7 because this 7 was not adjacent to anyone that left. More generally, in the next round, we only have to examine the entries that are adjacent to a node that left. And if we're able to do that in time that's linear in the number of entries to examine, so somehow we know to just skip along these entries to see if they should leave, then the total running time would be linear. And so there's many ways you can do something like this, although it's perfectly admissible to have an n log n solution. It's a lot simpler to implement that way. One of my approaches was to keep everything in a linked list. So if you imagine that this is just a doubly linked list, so the C++ standard library has linked lists built into them. When what you should do is for every candidate, you just keep track of their list iterator, for example. There's other solutions as well. And then when you remove someone, just look to the left in the linked list and look to the right and mark these list iterators as things to look at. So every round you can keep track of a pool of iterators you should examine. And as you delete things from the linked list, immediately you can tell what's left and what's right, even if those 2 candidates were initially very far apart from each other in the initial input. So that's one approach. I don't know, Howard, did you have anything different to say about your approach to it?
Not really. I just, I guess I keep track of my the left and right pointer of previous nicks myself without using any standard library, but it's essentially what you just said.
Yeah. And if you didn't have access to linked lists, you could have done it implicitly as well. You could have just kept track of indices that were still active. And then I guess when you remove something, the left and the right active, well, you can keep track of what's active to the left and what's active to the right. You can do it yourself, I guess, on top of an array. You don't have to use the built-in linked list data structure. But as long as you do something that only scans the entries that were adjacent to someone who was removed last time, then the total running time would be linear. Mine happened to be n log n because I didn't worry too much about the order I went through the iterators, but I still wanted to output them in their original order in the input, so I had some sorting. You could work hard and make it linear time, but n log n was good enough. Are there any questions about this problem? Okay. So pegs and legs, and this one, maybe the slides will be a nice reference for you if you go to implement this yourself later, but let me try to sketch this one out again as I did last time. So pegs and legs, the idea is you're playing this game and you drop a disc and it hits pegs and it has a probability of bouncing left or a probability of bouncing right, and bouncing left or right means it would bounce to some other peg from which it would bounce further until, well, ideally, until eventually it reaches a slot, which rewards you with some number of points. Well, in fact, maybe some bounce, well, here we go. Let me just draw, maybe some bounces end up in the same slot, and so on. Sorry, I'm just going to make sure that this is a complete example. So maybe it looks like this. So for every peg, you're told which pegs it would bounce to, and you're also told the probability it bounces left and the probability it bounces right. If that were just the problem, it would. Sorry, and the problem was to figure out which drop point would get you the best expected reward. So expected, of course, means the average reward averaging over the probabilities of going left and right. And you're supposed to figure out which slot would give you the best expected reward. So so if this was just the problem, it'd be a relatively straightforward dynamic programming problem. So if you were, that's the expected value from V. So I'm just going to write this in shorthand. The expected value you would receive if the disk hit a peg V is equal to the probability of going left times the expected value of, going left from V. So let's say this is V, this is X, this is Y, plus the probability of going right times the expected value if the disk reached peg Y. And that's a fairly straightforward the breakdown. Well, in fact, that's just by definition, I guess. But the problem is with this, it wasn't that easy. With this problem, the sum of the two probabilities of bouncing left and right could be strictly less than 1. And with the remaining probability, the disk gets stuck. So if you drop it, it will bounce until either it gets stuck on some peg or it reaches a slot. If it gets stuck, you're able to redrop it again. And your job is to figure out how you should play this game to maximize your expected reward when you finally reach a slot. And hopefully it's fairly apparent that in fact, there is some peg that you should keep playing that peg, because if the disk ever gets stuck, the history is reset. It's like you're at the very start of the game again. So if you chose a different peg because you think that's better, why didn't you do that from the start? So that's my intuitive explanation to say what you still have to do is for every peg, what's the expected value that you would receive if you played this game, given that if the disk got stuck, you restarted at this particular peg. So let's just very briefly fix a peg V. Let's figure out what's this value. If V is an initial peg, sorry, I should have clarified, some pegs were possible drop points and some were not. If V is a drop point that I'm going to play, I'm going to play it again and again and again until I finally get some reward. What is the expected reward for V? Well, the expected reward for V, so this is going to be saying we restart at V. And I'm going to change this quickly here to say U. This is the most mathy one, by the way. The other ones will be a bit more algorithmic. So this is a bit more mathy. So let's talk more generally. What's the expected value we would receive if the disk reached peg U, given that any redrop would come from V? So think at any point of the game, if you're playing peg V and the disk reaches peg U, let's figure out what's the expected value here. Well, it's going to be, maybe it'll make it to the bottom, or maybe it will be stuck, in which case you would restart. So it is, well, the probability you get stuck. So I said PL minus PR. And if you get stuck, you replay peg V again. You go back to the very top. Or you succeed in going left, in which case it is the expected value you would get from that peg X there, using the same notation as last slide, given that you would do any redrops at V. Finally, now the nice thing is if you unroll this thing, if you were to, so I'll just leave this as a little exercise for you, but if you unroll the definitions of these things, you can prove the following by induction, that this is equal to the probability we get stuck at some point under U. So given that we reached U, it's the probability we get stuck at some point and then reset. This is a little bit messy here. Plus, well, our original calculations, our naive calculations, X plus PR, times EY. So what am I saying here? What I'm saying is just take our naive calculations if the probability is sum to 1 in the easy version of the problem, and using this value here in this expression, the expected value we would get if the disk reached U, given that any restarts would be at V, is exactly this expression. So one final round of simplification shows us the following. Sorry, that's not what, in fact, we're done. Never mind. There's no more simplification. So let's think about the top slot again. It's going to be the PR that disk gets stuck. Given that it was dropped at V. So the probability just gets stuck overall times, well, our restart probability. Plus our, remember this old calculation that didn't have the subscript, it's just the simple naive recursive one. And this can also be calculated recursively. So if I just call this S of V, if I just call this S of V, then I just calculate S of V. That's the probability it gets stuck at V. Well, either it gets stuck here, or it bounces left but then gets stuck, or it bounces left and gets stuck. So if we calculate these probabilities, the probability of getting stuck, given that it reached a certain peg, then we just substitute that in here and we get our nice final expression, which is this. And then, like I said, the other presentations won't be as mathy, in case you're not enjoying this. Now, this doesn't really, because this is the value we're interested in. This was like our naive value, assuming it didn't get stuck. And this is the probability it will get stuck eventually if you drop it from V. I've just related this term to itself, but look, so we guaranteed that this would never, in fact, this would stay bounded away from 1. It would be at most 0.9999 or something like that. So you could just rewrite it this way. And 1 minus S of V. And that's it. This is a simple recursive calculation. This is a simple recursive calculation. This is the answer. So do it. Now, of course, it takes a little bit of insight and experience with probabilities to answer a question like this, but it was intended to be one of the harder ones on the set. So if you do this for every V and take the maximum, that is the answer. For every drop point V. I don't know what else there is to say about it. If you were to try to solve this just from the start, what you would do, I guess, is you would have to make the observation that there exists a single drop point, which you will always try restarting from there, that drop point, and then you would see how you would write down the expression that would calculate the expected value, and then you would have to work through some simplifications.
I have a question.
Yeah, 4 teams got this one. Yes.
I was going to ask, if we think about Markov chains, and if you analyze the probabilities and basically make a transition matrix, and then iterate that, would that work, though just take too long?
Yes, in principle. Okay, iterating that. So first off, yes, if you built a matrix that represents these calculations and just kind of iterate it multiple times, if I understand what you're saying, that would work, but it could take too long, or you could run into numerical issues at some point. The nice thing about this is it's just a single quick expression. We did see some teams that didn't build the Markov, like didn't build the matrix explicitly, but they somehow came about this idea, but then just at least initially didn't perform this simplification. So they just, given these values, they just kept trying to iterate this again and again, because if you enroll this, it'll be like an infinite series. But some teams got that to work and some teams didn't, and there's too much parameter tuning at play there. How far should you go with that? What's the right thing to do? Yeah, so in principle, your idea works. It would just be a bit slow, and you might run into numerical issues.
Yeah, there was at least one team that tried to unroll the infinite series somehow and then simulate it, and they were playing with the parameter to see how far to unroll it, and it was flip-flopping between wrong answer and time limit exceeded. As a judge, I was playing with the parameters too and managed to find the sweet spot that makes it work, but unfortunately the team never managed to find that sweet spot. But so maybe it's possible, but you have to tune this somehow.
Yeah.
I guess what I was saying is, if you build a transition matrix about if you drop a peg and you have or drop a chip, whatever it's called, in a certain spot, each spot has its own probability. Then the transitions take place, you get a new distribution. And you start off with a particular slot, one of the drop points, having all of the probability of being a 1, everything else is a 0. And you iterate that until it's fixed point. So then eventually they'll all end up in an ending point. And this is just kind of truncating it got stuck. So then you end up with a distribution that might not sum to 1, normalize it so it does sum to 1, use those as the weights. I was getting the correct answers on the test problems, but it was only ever iterating maybe 4 times. What do you think of that?
So again, I know what you're talking about, and that would work in principle. There were so many pegs and so many slots that I wonder, like if it's just hard to iterating that just so many times. I guess I don't know about the numerical issues involved in that one. And I don't know about how many iterations you would have to go to make it work out. This is a directed graph, and usually they're a little less kind when it comes to these Markov processes at converging rapidly, but maybe. I mean, our probability of getting stuck was bounded away from 1, but it was bounded away by like 10 to the negative 4. So I'm not sure. Yeah, so building dynamic. So let me look at that. We just did dynamic programming, building from the legs up to the drop points, tracking the benefit of each peg along the way, then compensating for it sticking at the end. I mean, that's probably that you've probably recovered exactly what I described. I tried a bit more of a holistic presentation, but maybe there was just too much notation in the way I did it. But like, if you look at my code, it's doing both that. I mean, ultimately what I said is we're just coming down to this simple calculation where these two things are recursively calculated. And it was a very long explanation justifying why this is the case. Okay, any other questions on this one? Yeah, so, okay, so the other ones were a bit more of the usual flavor that we're used to in these sorts of programming contests, although probability certainly is fair game. Paper snowflakes. This one had a nice little picture accompanying it. You start off with a long strip of paper, and then you fold it. So maybe it's long, but then you make a fold, then you make a fold, and you were told for every fold, you were told how far from the end of the strip of paper that's not affixed. Like this one end is affixed, and for each of these, you're told how far from the end of the paper is this fold. So the fold distances were strictly increasing, although they would overlap to something like this. Now you could easily calculate these points just by simulating the folding process. Just remembering where the most recent fold was, if you're folding left or right now. And then you can get the actual X coordinate. I'm sorry, I'm going to think of them as X values. There's no Y coordinate in this problem, but you can get all the folding points here. Then the second part of the problem was just some cuts are going to be made at various coordinates. And you're supposed to answer, what's the total length of all strips of paper lying between cuts? So in here, you would answer for these little red strips here I drew. Well, this problem has a relatively simple sweep line approach, but of course it takes some effort to see it. So the difficulty in this problem, I think, was solving it conceptually. Once you had that, it was not so bad to code, but that's easy to say once you've already coded the solution. Of course, we know it's difficult to come up with these solutions. So what my solution does is it sorts all of these different points by their X coordinate. So it sorts the folding points and all of the cutting points collectively in one large array. So I'm just drawing these, that each of these would be appearing in an array in increasing order of its X value. I'm going to think of a right fold, so something like this. I'm going to think of this as +2, meaning that as I sweep across this point, I'm going to all of a sudden see 2 more sheets of paper appear in this vertical span. I'm going to think of, well, the initial point is a +1, of course, +2. Now, I've got lots of these points here. +2. Then finally, we've got this. So I guess you can think of this as -4. My code would just put two identical things that were -2. But for the purpose of this, I'll just draw -4. Although my code would have two co-located -2s. -2, +2, -2, -1. So as I sweep along, meaning whenever I process one of these points, I'll just add this to some counter saying how many different folds are going to appear between here and the next event. And when I encounter a cut, I just sum I'm going to keep, as I go from one point to one event to the next, I'm going to take its length multiplied by the number of sheets that are there. And I'm just going to keep adding that up as I process events. So 2 times this length, and then as soon as I see a cut, I reset my running total to 0. So then after this cut, I'll continue doing 2 plus this length, plus 3 times this length, plus 5 times this length before this cut, and I will have added the total length of all sheets. And then I'll reset my running total yet again, and then just do 5 times this length here, and then 7 times this length. My example is pretty funny. And then 3 times this length. And the multiplier there is always being adjusted by these values. And so that's it. Yeah. So when I encountered a cut point, I just recorded the length that I had accumulated so far and reset the length. When I encountered a fold, I would just adjust my multiplier. And between events, I would just do the multiplier times the length between events. And that was it. Of course, at the very, very end here, there might be some, you're supposed to also output what's left here before the final cut. After the final cut. My code added a fictitious final cut really far down, which would, of course, accumulate a lot of 0, but that's okay. Are there any? Yeah, so I think if you followed this, the running time would be O of n log n, because once I sort the events, it's just going to take linear time to sweep through them. So the only thing that takes n log n time there is the sweep. We saw some other approaches that we didn't dig too much into, but we saw binary searches in the use of sets. So there might be alternative ways to view this, but this was my approach. Any questions? Okay, and let me wrap this up then with Antimatter Rain. And we did have one team solve Antimatter Rain. Okay, so the first thing we're going to do is we're going to assume all the x coordinates for Antimatter Rain are from 0 to like 3 times n or something like that. And the way you can do that is the x coordinates. Even though they could be arbitrary, we're just going to sort the unique x coordinates, and then compress them to 0, 1, 2, 3, 4, whatever they were originally. So we can assume that everything has a bounded x coordinate range. Okay, so I'm just going to leave that assumption out there. This is a technique called coordinate compression or grid compression, or I don't know what other people call it. Okay. Now comes the hard part of the problem. You had these sensors here, and rain droplets would fall and land on the sensors. And since this is antimatter rain, when a droplet hits a sensor, it obliterates the sensor and the droplet simultaneously. And there is a little bit of a tie-breaking thing to worry about. If 2 droplets hit a sensor at the same time, then all of the droplets that hit it at the same time will also be destroyed instantly. So they're instantly destroyed. The entire sensor will be destroyed the instant that the droplets hit it. So in this picture here, if all the droplets fall at the same uniform speed, so this droplet would hit this sensor before this droplet reached it. So then the sensor would be destroyed along with the droplet, and this one would continue falling. This one would also hit this sensor first. So in fact, this droplet, even though it had 2 sensors below it, would actually reach the ground. Okay, So here is a nice view of the problem that helps you solve it. You had to come up with this conceptual view first, and then decide how you could implement it quickly. Let's process the droplets and the sensors again in a bit of a sweep. So the two hardest problems had a bit of a sweep to them, but the way you did the sweeps were quite different. So by that, I mean, let's process the objects, the sensors and the droplets one at a time from top down. Let's talk first about what happens when you process a sensor. When you process a sensor, you're first going to ask which droplet that's still alive will hit the sensor first. And so if you can answer that, which droplet would hit the sensor first, you know that that droplet in the sensor would be obliterated. But then you can ask, well, if I got rid of that droplet, would the next droplet hit it at the same time? So you just have to keep finding the next droplet that would hit it until finally you hit one that is higher. Maybe there's a higher one up here. So if for a sensor you can compute the next droplet that will hit it amongst all the alive droplets, then kill it, and all other droplets at the same height that would hit it. And that's really the problem. So you just go down. For every sensor, you process the droplets. When you process these droplets, kill the sensor, you remove the droplets from your set of alive droplets, and you record the height that they died at. And any droplet that's never killed, of course, has a height of 0. It hits the ground. So that's, how do you answer that question quickly? Given a sensor, how can you quickly answer which droplets will hit it? Well, there are, again, a couple of related approaches to this, and the team that solved the problem took a slightly different approach than I did. But one of the things you could use is a segment tree, which is a fairly standard data structure in contest problems that lets you answer questions about a range. So a segment tree stores values in, maintains an array and lets you answer queries about that array. So let's say you had values in an array. So let's ignore droplets for now. Let's say you had values in an array and you wanted to answer questions like, in this range, what's the minimum value? I'm not going to talk about how segment trees work. There's a lot of wonderful resources out there that can explain it much better than I can in a quick presentation. But if you use one of these things to figure out which given a range, what's the least value, then you can do the following thing. Given this range here, amongst all the droplets that we've processed so far, so we're only going to have the droplets that we've processed so far represented in our segment tree, which amongst all those in this range here, which one has the lowest Y value? So you find it, you eliminate it, and then you'd ask the question again to see if the next one still has the same Y value, so you can eliminate all the ones that'll hit at the same time. And that's the essence of the problem, I guess. I should point out that the segment tree can be updated dynamically on the fly. So you can update any of these values, and then with the segment tree in log n time, you can update the entire segment tree so that the next time you ask a query about a range, it'll be accurate. So for every droplet you encounter, you look at the X coordinate. So we're going to build a segment tree over the X coordinates, which is why we compressed the grid. So for every droplet, you're going to update in the segment tree that minimum max value. When you remove a droplet by destroying it, so let me update this picture quickly. When you remove a droplet by destroying it, you have to update that X again. Now here's the one last simple ingredient. Everything is much harder than this last simple idea here. You should also keep track of maybe a stack of the drops that you haven't dissolved yet at this point. So once you destroy this droplet, you look, is there another drop in the stack? If so, then you update the segment tree at that location. So this is a very intricate use of a segment tree, I guess. It is just a segment tree problem, but it's certainly not one of the easiest ones out there. We were happy to see it solved. The team that solved this problem, instead of using a segment tree, they used a sparse table, which if you're familiar with that, it's easier to implement than a segment tree, but the running time is a little bit worse, although still fast enough for this problem. So the running time of our solution was O of n log n, where n is the total number of objects in play. Oh, and Ian says they also scan from the bottom up. I have to think about that. Maybe that would be equivalent. It made it more complicated. Okay. Whereas if you used a sparse table, it would actually run in time, well, n times root n, but it's a very skinny root n. Like the big O here is really skinny. So you could make this work out. So this is the guaranteed solution that you know will work. This takes a little bit of parameter tuning, but you can get it to work as well. Okay. Thanks so much for sitting through my version of the talk here. The actual PDFs will be posted. I know I didn't dwell on them very long. I figured I'd do a little whiteboard presentation instead, but these will be posted to the Discord channel.
Thanks, you two. That was great. I suppose if people have questions, of course, I'll also say we will attempt to upload a video. This is a recording. This is a recording. And actually, Howard, I apologize. We forgot to hit record until like the first one that felt a little harder. So hopefully that's fine. So I think
not a problem.
And so
we'll post the solutions anyway.
So yeah, there'll be posted solutions, the slides, and then a link to this video, I hope will all be available to the teams that are interested.
Yeah, I'll even take it one step further and tell people that if you're working through one of these problems and you're still stuck on something, you can just well, this offer is exclusive to our MRC contestants only because I don't want the world to poke me about it. But you can just poke me on Discord and let me know that you've been working through something, but you're still stuck. I'm happy helping you work through it.
I guess I've been trying to sell this a little bit. There's a section called POW for Problem of the Week on IO. If a team or students want to work on that, maybe that's a place where they could pick one off and just discuss it, whether it's part of a judge's participation or not. Okay, thank you for going through that. That was fantastic to really get to see how the how some of those are or could be solved. As a student, I guess the one thing that I get, well, everybody sort of pointed out, there's often more than one way to do it. So it's a nice thing to realize that there's not only one correct solution to a lot of problems, but having the right tools around to find one of them is a great idea. All right, so now I think it's time to hit the resolver, see if we can make this work. Let's see. Wish I could do a drum roll, but I can't. Let's see here. Access. What? Let's see here. Do this. That's going. My Zoom. Interesting. I'm glad I have two screens. I need one to bring my Discord on one in order to launch the Zoom thing on the other one, or the resolver on the other one. There's probably another way to do this, but let's see. This seems to work. Share screen to that one and share. Are people seeing the resolver? It says something about Rocky Mountain Regional Contest at the top, or not?
Yeah, you're good, Warren. It's Sean.
Okay. All right. It just looks a little funny on my side. I will assume this is working. So, and where's my mouse? Right there. Oh, okay. One more try. It died. Let's see here. So I am. So let me just share that screen first and then see if I can launch it to resolver afterwards. 22. Oh, I did that wrong. Just got to the same spot. There. Stop share. Okay, are you guys seeing like desert?
Yep.
Yes. Okay. Let me try to launch this as a resolver. Okay, are you seeing resolver? Ah, I can't click on it. Okay, I just got this started, and I guess I lost my sequence to make this all work. New operations. Okay. Maybe if I bring this window, okay, maybe this will work. Okay, I'm on the right screen now. Maybe if I launch it from the same screen. Sorry guys. It keeps dying and I'm not sure why. Let's see here. Okay, I'll take this out. Maybe I'm gonna take the stepping off and I will just try to talk fast as it's moving along. Okay, can you see it?
Yes, sir.
Okay, I'm sorry. I thought I had this going and you guys don't really want to see the front page all the time. There, finally, spacebar works. Okay, so here's the entire play, I believe, at an hour before the end of the contest. And we'll go down to the bottom and see what happens as the contest proceeds. So here goes. So team 3, no new solutions, no new solutions. Team 4 tried that problem, but it was false, and so it didn't move forward. Team Alberta, sorry, I didn't see which one they got finished. Lethbridge got 5, not right. No new solutions. Alberta Black, no new solutions. No new solutions. Up and up. Move up. I miss no new solution. Nope. Okay. The decks. Nope. Yup. So the money is 8. I will remind the teams. BYU. $16. Air Force. Oh, nope. And yes. Oh. Really? Program terminated by mouse click. This is a pretty, okay, now I have to figure out how to get this started on that step. My apologies for data. So I'm trying to see if I can find a command line option that lets us jump to the place we want. Display. Oh, interesting. Spacebar reserve. Okay. Go forward 1 resolution step is R. Okay. Here we go. Avoid the spacebar. Spacebar is bad. Okay. I'm not sure why we need to watch this one. I'm afraid to click on anything. When is this? Rewind. Restart. Go forward. Rewind. Restart. Jump to beginning. Okay, this claims number 2 is amazing. 2. Okay. So then now R is one step forward. And I'm afraid to click. think I've lost my mouse focus. Not space. Clicking on the screen kills the resolver. This does not seem great.
Often you can use Alt-Tab to toggle the focus between windows.
Thank you. Let me see if I can get to, okay. Except for today. Shift tab, Command tab. I am not getting to this one. Huh. Nope. I think if I click on it, yep, goes away. That is not the best choice for user interface. Sorry to say. Single step. Okay, I'll take away the single step and see if we can get it to play for us. That way. I hope I have 0. 0. Okay. Please move forward. I'm afraid to type a key. 1, 0, R. No. Presenter. Jump 1 step forward. 1. If I click on it, it's going to go away, and then I don't know how else to give it focus.
Some people are saying to try Command Tab on Mac.
Not bringing anything up for me. Interesting. Alt tab, Control tab, or maybe because I'm in a browser. Nope. Nope. Yeah, I remember an Alt tab being the way it works, but not today. It was not bringing up anything but that. And then if I click on it, it goes away, so I can't get focus back onto the display. Well, that is very unfortunate that this resolver is not, yeah, I'm gonna click on it and off it goes. So close. One heel click away. All right. Solver, display to.
Or if you tried it from one display, if you just kind of turn the other one off and then just tried it from your single display, would it automatically get the focus?
Okay, let me try that. Declare the display parameter. And go. Okay, can you guys see it? That?
You need to share your screen again.
Oh, but see, now I can't get to the screen share because it's all one. Okay, let me try to share screen to this screen. Let's see if we can get this. Oh, my apologies. Thought we had this working, but this is how it goes. Desktop one, share, terminal, up. Remarkably small for some reason. I don't know why. Can you see that?
Yes.
Okay, 0, nothing. I don't know if I have actually focus on the application, and I'm afraid to click because apparently the click makes it go away. EAS. How? Oh, did something. Maybe? Okay. Okay, I will not touch anything. We're gonna just watch this go for a little while. Don't touch anything. Orange. Turquoise. So I don't quite remember where it all fell apart the first time. It was about 15, right? Bronze. Up we go. I am not sure what happened, and I'm afraid to type anything. It looks like it stopped again. Interesting. Okay, I'm gonna try the space bar. If this works. Yay! Never been so excited about a space bar. All right. 10. University of Utah.
So are these the final results, or is it like what's this updating? Like what's the update order, and when
The
will the
update
final
order
be released?
Is in the order of submissions by teams, from the lowest ranking team at an hour before the contest. So you look at the hour before the contest, and then the lowest ranked team, you look at their progress, and if they made any progress that moved them up, that progress is played out, and then moving forward through that. So it's a playback that looks at essentially the bottom of the scoreboard up. Does that help?
It does. It does. Yeah. So when will it get to the end and we can see the final results?
We are getting there now.
I am so excited. Nervously.
Yeah.
Bronze medalist. Yay! Solve 6 problems.
So just so people know, the medals here are because at the ICPC World Finals,
Yes.
top 4 get gold, next 4 get silver, and next 4 get bronze. Is so
this is not our resolver. It is but that is great. So bronze medalist solved 7 problems. Fantastic. BYU cares. Nice. Next, bronze medalist. And up we go. All right. So, I mean, this is sort of, are you in the money or not? We will not, again, I'm not guaranteeing that 8 teams will be promoted unless you're all from the same campus. I don't see that going on. University of Calgary. So you're at slot 9. So everyone, as far as I understand, 8 and above. So this is a shuffling of the deck, but everyone 8 or above should be promoted unless are there 2 teams from the same campus? Or sorry, 3 teams from the same campus would be the question. I do not. I see 2 Albertas. I see 2 Utahs. University of Lethbridge, Calgary. I believe everybody in this slot has now can be comfortable in thinking that you will be invited to the next tier. Utah. So congratulations, everybody who's up here in this group. And yes, it is fun to see who how the last group is shuffled. And at the higher tiers, there will be not nearly as many like promotions. So the play will be much higher up in the game. University of Alberta, congratulations. Lethbridge. Nice. BYU Ints. Nice. University of North Texas, our guests did quite well, I will say. Just great. College School of Mines. The school championship is just a vague thing that doesn't really mean anything in this contest, since all the sites were everywhere. People just picked what they wanted to register. BYU gold medalist, congratulations. And Alberta, well, I think everybody knew Alberta was in the money because that actually happened before even the scoreboard. So we knew where that one was sitting. So there they are. So 1 through 8 is the, and these are the final standings. There's hopefully a short discussion to see whether there's any more than 8 that will be invited forward. But everybody just, congratulations. I hope you enjoyed the contest. It doesn't, part of me, like, I hope you enjoyed this contest. And if you are going to be promoted or you are promoted, then that's super. And I hope you enjoy the next year. Is there any more questions? Okay, I will press escape. And just thanks everyone. Congratulations. Hope you enjoyed the contest and look forward to seeing your participation next year.
And Warren, we would like to say a very big thank you to you for all of the coordination that you're doing with this and also with the broader ICPC community too. Thank you so much.
You're welcome. It has been a fun part of what the things I get to do. I really appreciate it. All right, everybody, enjoy your evening. Go ahead and shift your conversations hopefully to IO if you have would like to keep talking about problems. And Ram and Ryan, I hope we'll get together to get a recording of these posted somewhere. Especially, I think the most interesting thing, of course, is to look at the judges' reviews of the problems for anybody's interested in that stuff. Any other last comments?
And we will also be posting the judging solutions at some point, right? We usually
That's
post
correct.
the judging
We
solutions.
take the entire data set, solutions, and everything and post it on a public repo hosted through GitHub. And so you will get to see all of that, hopefully by the end of this coming week. Okay, everybody, thanks again, and just have a great night and enjoy the rest of your weekend.